first quarterly film report on the Saturn V, designated by the National Aeronautics and Space Administration as the vehicle which will launch the Apollo spacecraft to accomplish circumlunar flight and manned lunar landings. The Saturn V booster, or first stage, identified as the S1C, is now under joint development by the George C. Marshall Space Flight Center and the Boeing Company. It will have 5 F1 engines producing a total thrust of 7.5 million pounds. Rocketdyne Division of North American Aviation is contractor for the F1 engine. The second stage, S2, is under development by the Space Systems and Information Division of North American Aviation. Its 5 J2 engines using liquid hydrogen will generate 1 million pounds of thrust. Rocketdyne is also contractor for the J2 engine. The third stage, known as S4B, is being developed by Douglas Aircraft Company. It will use a single engine, J2, with a thrust of 200,000 pounds. Designed to carry 3 men, the Apollo spacecraft will ride atop the third stage to complete the Saturn C5 space vehicle.
This report will highlight major facilities build-up activity for manufacture and testing of S1C, S2, and S4B stages. At the Marshall Space Flight Center, where overall direction of the Saturn program emanates, and where ground test S1C stages will be assembled and tested, some plant facilities are now being rapidly reoriented from the C1 to the C5 program. For example, entrances to the fabrication and assembly buildings had to be considerably enlarged to allow movement of the vehicle. A new components transporter is being assembled at Marshall for use in moving various S1C parts, such as bulkheads and tank sections, from one area to another. 32 feet tall, the transporter will carry its loads suspended from hooks on cables at each side. Adjacent to the fabrication area at Marshall's Manufacturing Engineering Division, construction has begun on an S1C combination vertical assembly station and hydrostatic test tower. The 160-foot tall structure will also be used for cleaning of finished tanks. Located near the present Saturn C1 dynamic test stand will be a 360-foot high C5 dynamic stand for which design work has been completed. A dynamic test vehicle assembled at Marshall will be suspended in the tower and vibrated to determine simulated in-flight responses. Work is progressing on construction of the static test stand to be used for captive firing S1C stages. Work on the test stand foundation and control center has been underway for several months. And a contract has been awarded for construction of the tower itself, which will measure 160 feet square at the base and stand 405 feet high. A contract for excavation and other preliminary work on Marshall's single F1 engine static test stand has also been awarded, and test stand design has been completed. The stand will be approximately 200 feet high. 2 full-scale fiberglass mock-ups of S1C locks and fuel tank bulkheads have been received by the Marshall Center from Boeing Company's plant at Wichita, Kansas. They will become part of the S1C mock-up to be assembled at Marshall. Consisting of 8 gore segments, the bulkhead is 33 feet in diameter and 10 feet high at the center. Bulkhead fabrication fixtures, such as this device for cutting and welding gore fitting connections, are now being installed at Marshall in preparation for fabrication work. All the fixtures were provided by Boeing Wichita. This gore trim fixture trims the top edge of the base and the bottom edge of the apex of each gore in order to make a joint to weld the two pieces together. Portable vacuum chucks or holding devices keep the gores in place while they're being trimmed and welded. Base and apex portions are joined on this gore welding fixture. Its welding platform is mounted over a pit and can be tilted 30 degrees, making it possible to weld uphill at all times. Welding downward is undesirable because the weld will run off instead of puddling, as is necessary to form a strong weld. This meridian edge gore trim fixture is used for trimming the gores lengthwise. A large vacuum chuck from which air is evacuated by a pump holds the gore during trimming. Gores are then placed in this bulkhead assembly welding station, where meridian welds are performed to join them together. The process is repeated 8 times to make a bulkhead assembly. After each gore is welded, the turntable welding platform is rotated 45 degrees to position the next gore for the weld head, which remains in place. This fixture is used to trim each bulkhead assembly to a 54-inch diameter opening at the top, and then weld in the bulkhead closure piece to complete the bulkhead fabrication process. At Wichita, Boeing's 80-acre Plant 2 area is the site of the company's program for Saturn C5 support tooling and fabrication work. Preliminary milling on C5 booster test panels was accomplished on these tape-controlled skin mills, with working length and width of 90 feet and 12 feet respectively. The same skin mills will be used for pocket milling required on the tank end gore segment, and also for milling integrally stiffened tank skins. Fiberglass molds or layups are being formed here for the tank end gore segment bulge form dies. 8 such segments will form the ends for fuel and LOX tanks for C5 boosters. The master form for the segment is fabricated of plaster. Other Saturn layups are made of fiberglass. One such fiberglass mold is this base gore segment. Welding on all tools to be used in Boeing's fabrication of parts for the Saturn C5 program is performed in the Boeing Wichita Weld Shop. This section represents the framework for the base portion of the bulge form die for tank end gores. Wire feed welding equipment and other advanced fabrication techniques are employed in all areas of Saturn work at the Wichita facility. At Marshall Center's Michoud operations in New Orleans, the huge plant is being readied for assembly of C5 flight boosters by Boeing. When NASA occupied the former Army Ordnance Plant, its overhead superstructure, used in manufacture of tank engines during World War II, was too low for Saturn booster assembly. Plant renovation, performed under contract by Mason Rust Company of New Orleans, consisted largely of removal of the surplus overhead grillage, such as rails, cranes, and heat ducts. Their removal now allows an overhead clearance of 40 feet, which will provide 6 inches of clearance for the booster in the horizontal position on its transporter. Approximately 2,000 tons of steel were cut out of the overhead superstructure and hauled from the plant to be sold as scrap. A 50-foot diameter hole had to be broken in the floor in preparation for a specially constructed foundation for Boeing's massive 100-ton boring mill. A wooden retaining wall with steel spider reinforcement kept the sides of the 15-foot deep excavation from caving in. The old piling on which the original floor was mounted was cut off at the bottom of the hole and augmented by an additional 116 new piles, which were driven 30 feet into the ground. A concrete cap was then poured on the piles, and the foundation built up with concrete and reinforced steel. The boring mill was shipped to Michoud on 8 flat cars from the Army's Detroit Arsenal, where it was formerly in use. Steam cleaning of the mill was accomplished after its delivery to the Michoud plant. Emplacement of the mill on its foundation required extreme care to ensure proper meshing of gear systems. The turntable, weighing over 70 tons, was not large enough for Saturn's needs, so extensions were manufactured to increase the diameter by approximately 12 feet. At Ingalls Shipyard in Pascagoula, Mississippi, rolling of aluminum ingots for Y-ring segments of S1C stages was recently performed for Boeing. Y-rings will be used to connect bulkheads to fuel and LOX tank skins. In order to check for cracks, dye-penetrant tests were performed on ingots before, during, and after the rolling operation. Ingots measured 5 inches thick and 34 feet long. The desired final radius of 16.5 feet was obtained by rolling a little at a time and checking it by hand with a plywood template. During rolling, smooth metal collars were placed on the heavy hydraulically operated rollers to prevent scarring the ingot. A test ingot, after its normal rolling operation had been accomplished, was replaced in the rollers and then rolled beyond 360 degrees in a checkout attempt to break the ingot. Even at this extreme overbend, however, no breaks occurred. The ends of normally rolled segments were machined at the shipyard to an approximate V point. When the 3 segments which form the Y-ring are placed together for welding, the points of the V's touch, and the open V's, formed both inside and outside the ring surface, are filled with metal to form strong, heavy welds from the center out. In an interim weld facility set up at Michoud, welders were trained to operate the automatic machines used to make the Y-ring welds. Sonic and X-ray testing of welds was conducted to discover any flaws or cracks. The first actual Y-ring weld was performed in Boeing's production weld facility in December, using personnel and equipment formerly certified in the interim weld facility. The boring mill at Michoud was put to its initial use in a test operation to machine the first Y-ring segments to finished dimensions. One segment was cut into small sections for test pieces, which will be used for experimental welding to determine if the Y-ring can be welded after it is machined rather than before. Following the tests, the 3 segments will be welded together to determine the feasibility of welding the completed Y-ring. Construction of the foundation for the new vertical assembly building at Michoud is now well underway. The building will have 3 tank assembly areas, 1 chemical tank test area, and 1 stage vertical assembly area. At Rocketdyne, where Saturn's F1 engines are being developed, inspection of the engine's modified 16-to-1 thrust chamber extension skirt after its first short-duration firing showed that collapsing and longitudinal buckling have been eliminated in this design. A new exhaust manifold now being employed on the F1 is smaller and more circular in shape than the previous design. This configuration is intended to reduce the axial loading on the skirt support flange, which results in membrane stresses in the manifold shell. Rocketdyne's new Model 1 LOX pump has been undergoing tests at Santa Susana. In this test setup, a pipe is connected to the top of the pump, permitting testing with a direct flow. Pump performance is then compared with performance when the pump is flowed through the normal inlets in the elbows. The The F1 heat exchanger, designed to provide pressurization for the LOX and fuel tanks, has been tested a number of times at Components Test Lab number 3. Several injector designs, such as this LOX dispersion injector, have been tested in an effort to increase combustion stability margins. Other designs tested include the baffled divergent ring injector, low-fuel Delta P injector, 21-compartment baffled injector, and the divergent ring injector. As part of the LOX dome oscillation study, tests have been conducted on Rocketdyne's high-flow test bench at varying pressures. This data will be evaluated and compared with data from hot testing. A full-scale F1 engine mock-up has been delivered by Rocketdyne to the Marshall Center, where it was mounted vertically for tests in a gimbaling stand. Later, it will be mounted in a partial mock-up of the S1C thrust structure. Final assembly of Saturn S2 stages will be accomplished at the new Seal Beach, California facility of North American's Space and Information Systems Division. Construction began in August. S&ID personnel occupied a portion of the facility's bulkhead fabrication building in December to coordinate tooling installation. This 1:48 scale model of the Seal Beach vertical assembly facility is being used to evaluate proposed S2 assembly sequences and to check integration of tools, facilities, material handling devices, and booster components. Production tooling for use at Seal Beach in assembly and welding of S2 bulkheads is now being fabricated at S&ID's Downey plant. Delivery of weld tooling will begin in February. Construction of S&ID's El Toro facility for high-energy forming of bulkhead gore segments and high-energy sizing of bulkheads has been virtually completed. A master mold for bulkhead gore segment tooling has been used at Downey to form a master facility tool, an overpress template, and soft tooling for the high-energy forming program at El Toro. High-energy forming dies are being machined from rough-formed steel using skate machining techniques. These dies, due to their size, shape, and weight, could not be machined by conventional methods. In February, the forming dies will be delivered to the El Toro facility for use in high-energy forming. Another major construction activity underway for the S2 program is preparation for a new static test stand called COCA 4 at Santa Susana. The COCA 1 test stand is also being modified for S2. A quarter-scale S2 test tank has recently been fabricated and hydrostatically tested at Downey to prove the design integrity of the insulation system. A quarter-scale working model of one of the 3 umbilical arms required to service the S2 stage has also been completed. Cornell Aeronautical Laboratory in Buffalo, New York, has concluded a series of tests for S&ID to determine the S2's base environment in terms of temperature, heating rates, and pressure distribution, and to establish the optimum deflector and shrouding arrangement for the stage's 5 J2 engines. Using a 1/25th scale model, tests were conducted at a pressure equivalent to an altitude of 240,000 feet. At Douglas Aircraft Company, where design, development, fabrication, and testing of the Saturn C5's third stage, S4B, will be accomplished. Structural layout drawings being prepared by Douglas are nearing completion. And work is underway on detailed stage structural drawings. At Douglas Sacramento Test Area, where static tests of the Saturn C1's S4 stage are conducted, a new facility for ground testing of the larger S4B stage is being planned. The complex will include static test stands, a blockhouse, propellant and high-pressure gas systems, and supporting utilities. At Rocketdyne's Santa Susana area, buildup of test facilities continues for the J2 engine, common to S2 and S4B stages. Vertical test stand number 2 is almost complete. At Delta test stand number 2, which will be used for 500-second runs, outside LOX run tanks are in place, and fabrication of the 90,000-gallon liquid hydrogen run vessel is virtually finished. A hard mock-up of the Block 3 J2 engine has recently been completed. Oriented to vehicle requirements, it represents the initial flight readiness engine. Since the J2's first long-duration static test on October 4th, 1962, in which the engine fired for more than 4 minutes at full thrust, a number of similar tests have been successfully conducted. Saturn C5 vehicles will be launched from Complex 39 in the new NASA area, for which land has been acquired north of Cape Canaveral. Complex 39, covering 30,000 acres and containing 2 or more launch pads, will embody a new concept in launch facilities. Saturn vehicles will be completely erected and checked out in a 48-story tall vertical assembly building about 3 miles from the launch site. The building will contain 4 bays, in each of which a Saturn can be erected, mated to the Apollo spacecraft, and checked out on a launch rack, which also supports its 400-foot umbilical tower. The launch-ready Saturn will then be transported to the launching pad by means of a 2,500-ton crawler vehicle. At the pad, the 20-foot-high crawler will employ its hydraulic cylinders to lower the rack and vehicle onto the launch platform. Launching of the Saturn C5 from Cape Canaveral will be a giant step in the lunar orbital rendezvous procedure, which has been chosen by NASA as prime mission mode for a lunar landing.